Hi everyone! Our new series of SRv6 BE related courses is attracting a lot of attention. Starting from this course, we'll introduce SRv6 TE Policy, where TE indicates traffic engineering. SRv6 TE and SRv6 BE are two different forwarding modes. SRv6 TE Policy, which is also called SRv6 Policy in some scenarios, supports common services on the live network, such as BGP L3 VPN, EVPN L3 VPN, EVPN L2 VPN, and public network IP services. SRv6 TE policy configurations are similar for these services. Before we introduce the corresponding service scenarios, let's talk about the implementation of SRv6 TE policy. This course focuses on the SRv6 TE policy model and its advantages. We'll also briefly introduce how to configure SRv6 TE policy and verify the configuration. Now let's take a look at the SRv6 TE policy model. Before this new service model emerged, MPLS TE tunnels were commonly used. These tunnels adopt a two-level model that mainly involves two elements: destination address and the tunnel ID. The tunnel ID identifies an MPLS TE tunnel. If the next hop of a route matches the destination address of an MPLS TE tunnel, the route can recur to this tunnel. The route recursion mode, however, is relatively coarse. In VPN scenarios, the next hops of the routes that belong to the same VPN instance may be the same PE on the public network. In this case, the routes will recur to the same MPLS TE tunnel, meaning that services cannot be differentiated during forwarding. For example, in this VPN, some services need to be forwarded over a low latency path, while the others need to be forwarded over a high bandwidth path. The MPLS TE tunnel model cannot meet these requirements. The second level model of MPLS TE tunnels is LSP. The primary and backup LSPs work in backup mode but cannot implement load balancing. In contrast, SRv6 TE policy is a three-level model involving three elements: head-end, endpoint, and color. The head-end element is implicit. For example, a node on which an SRv6 TE policy is configured is called the head-end. If a controller delivers an SRv6 TE policy to a forwarder, the forwarder is also considered the head-end. As such, the head-end is implicit and does not need to be explicitly configured or specified. Another element is endpoint, which refers to the destination address of an SRv6 TE policy. The third element is color, which helps to implement refined traffic steering. The color attribute identifies the characteristics of the SRv6 TE policy, such as whether the SRv6 TE policy's path features a low latency or high bandwidth. We can also configure the color extended community attribute for routes. For example, we can specify a color value to identify a low latency for services that require low latency paths, and another color value to identify high bandwidth for services that require high bandwidth paths. During route recursion, the device first matches the color value of the involved route against the color value of the SRv6 TE policy. It then matches the next hop of the route against the endpoint of the SRv6 TE policy. If the matching succeeds, the route can successfully recur to the SRv6 TE policy. This allows different routes to recur to different SRv6 TE policies based on the color attribute. The second level model of SRv6 TE policy is candidate path. A SRv6 TE policy can contain multiple candidate paths that have different preferences. The candidate path with the highest preference functions as the primary, and the other paths provide protection. Each candidate path can be configured with multiple segment lists, which are forwarding paths represented by a list of seeds. Segment lists can carry different weights and implement equal cost or unequal cost load balancing based on these weights. In addition, a binding seed can be configured to represent an SRv6 TE policy when the policy is invoked by other policies. Binding seeds can be combined with common end and end.x seeds to form new SRv6 TE policies. They are commonly used in inter-AS scenarios. Next, let's look at the advantages of the SRv6 TE policy model. The first is its ability to support flexible traffic steering thanks to the color attribute. This attribute defines an application-level network SLA policy, enabling flexible traffic steering for different services. With the color attribute, for instance, we can steer services that need a high bandwidth path to a high bandwidth SRv6 TE policy path, and services that need a low latency path to a low latency SRv6 TE policy path. The entire process is completely automated. Carriers can quickly meet users' SLA requirements to build new business models. Load balancing is another advantage of the SRv6 TE policy model. As we mentioned previously, load balancing is mainly implemented among segment lists. The SRv6 TE policy model also offers high reliability by supporting multiple protection technologies that play an important role in constructing a deterministic IP network. Let's look at these protection technologies in more detail. They are classified as local protection, which mainly includes TILFA and midpoint protection, or end-to-end protection, which mainly includes hot standby, VPN FRR, and SRv6BE protection. Hot standby protection uses a backup candidate path to protect the primary one and needs to work with BFD. VPN FRR protection uses one policy to protect another and also needs to work with BFD. And SRv6BE enables traffic to be switched to an SRv6BE path for forwarding if all policies become unavailable. However, SRv6BE forwards traffic over the shortest path, which cannot guarantee the SLA of services. Let's take a closer look at the differences between these protection technologies. First, let's see how TILFA is implemented. In this example, the segment list is P3, PE2, which does not include P1. If P1 fails, TILFA can be used to steer traffic through P2 and P4. However, if P1 is included in the segment list, TILFA becomes invalid. Because P1 is a hop in the segment list, it cannot be bypassed. As such, traffic detoured to P2 will be forwarded back to P1, leading to a forwarding failure. This prevents TILFA from taking effect. In this scenario, midpoint protection can be deployed to bypass P1 and directly use the seed of P3 as the new destination address for forwarding. In hot standby protection, a backup candidate path is used to protect the primary one. In this example, the endpoints of the two candidate paths are both PE2. And for VPN FRR, it uses a backup policy to protect the primary one. Now let's look at an example to understand how VPN FRR is implemented. CE2 advertises a route to P2 and P3, and both PEs then advertise the route to P1. This means that there are two routes from P1 to CE2, resulting in two next hops. The two routes with different next hops recurs to these different policies, forming VPN FRR protection. VPN FRR differs from hot standby protection because it involves two SRv6 TE policies with different endpoints. The last protection technology we'll look at is SRv6BE. It enables traffic to be directly switched to a SRv6BE path for forwarding in best effort mode, if all SRv6 TE policies fail. Now that we are familiar with the SRv6 TE policy model, let's see how to configure an SRv6 TE policy. An SRv6 TE policy can be either delivered by a controller or manually configured. If a controller is used for delivery, it needs to establish a BGP-LS peer relationship with the desired forwarder to collect network information for path computation. Such information includes the network bandwidth, cost, latency, and affinity attributes. After computing an SRv6 TE policy path, the controller delivers it to the ingress through the BGP-SR policy peer relationship. The ingress then generates an SRv6 TE policy based on the received BGP update message. Functions such as global traffic optimization and resource reservation are supported in controller-based delivery mode. The other way is to configure a path manually. Let's look at an example to see how we can configure a path. This example uses a network topology with 4 devices that belong to the same AS. A bidirectional SRv6 TE policy is needed between P1 and P2 to carry services. For the SRv6 TE policy on P1, the primary candidate path is shown in green and the backup is shown in blue. These 2 paths form a protection group. The configurations on P2 are similar to those on P1. Now let's see how to configure an SRv6 TE policy. The first step involves configuring ECs to achieve basic route reachability. This is because SRv6 is implemented through ECs extensions. EC's configuration consists of global and interface-specific configurations. The configurations on the 4 devices are similar. The next step is to perform basic SRv6 configuration. This involves enabling SRv6 globally, configuring a source address for SRv6 encapsulation, creating a locator, and configuring seeds in the locator range. Because SRv6 TE policy path programming requires AND seeds representing nodes and AND.X seeds representing adjacencies, we typically need to configure the 2 types of seeds. Here we configure 2 AND.X seeds on P1. One AND.X seeds is for the P1 to P1 adjacency, using an interface on P1 as the outbound interface, and P1's interface address as the next hop. The other AND.X seed is for the adjacency from P1 to P2, using another interface on P1 as the outbound interface, and P2's interface address as the next hop. The configurations on other devices are similar to the configuration on P1. After the configuration is complete, we need to enable SRv6 in ECs and configure the device to advertise the locator route. Because AND.X seeds have been manually configured, we can disable ECs from dynamically generating seeds. In SRv6 TE policy scenarios, the seed dynamically generated by ECs will change if a device or protocol restarts, causing the SRv6 TE policy to fail. This is why manual seed configuration is recommended. We can use commands such as opcode to configure static seeds. Now that we have completed those configurations, let's look at the SRv6 seed table using P1 as an example. The command output shows that P1 has generated 2 AND.X seeds, and each of them is bound to an outbound interface. The figure on the right shows the seeds configured for the network, and the arrows indicate the directions of adjacencies identified by the seeds. These seeds will be used to orchestrate SRv6 TE policy segment lists. The locators and seeds we configured earlier are advertised through EC's LSPs. In this example, we can see the SRv6 locator and AND.X seeds carried by the LSP. Because AND seeds are not configured, the LSP does not carry relevant information. ECS generates an LSDB based on ECS LSPs and runs the SPF algorithm to calculate routes. The command output shows that P1 has learned the locator routes of P1, P2, and P2, and P1 has also learned locator routes. The seeds are routable, because they are allocated within the locator range. Next, let's configure an SRv6 TE policy. We start by configuring an explicit path through the segment list command. Then we specify involved hops, such as one end.exceed identifying the adjacency from P1 to P1, and another one identifying the adjacency from P1 to P2. Next, we create a backup segment list and specify two hops, that is one end.exceed identifying the adjacency from P1 to P2, and another one identifying the adjacency from P2 to P2. At this point, we have created two segment lists. The next step is to create an SRv6 TE policy in which the endpoint is a loopback interface address on P2, and the color value is 101. We also need to specify the primary and backup candidate paths in the SRv6 TE policy. In this case, the primary candidate path of P1 is P1 to P1 to P2, and the backup candidate path is P1 to P2 to P2. As such, we need to specify the corresponding segment list to be referenced by the candidate path. The configurations on P2 are similar to those on P1. After configuring the SRv6 TE policy, we can verify the configuration. To do so, we start by checking the state of the SRv6 TE policy. The command output shows that the policy state and the administrative state are both up. There are two candidate paths under the policy. The candidate path with the preference of 200 is the primary, and the path state is active, and the segment list state is up. The candidate path with the preference of 100 is the backup. Although the path state is inactive, the path is still valid. In addition, although the segment list state is down, the segment lists are valid. Reliability functions such as SBFD, one-arm BFD, and hot standby can be configured for the SRv6 TE policy. If such functions are configured, corresponding states will be displayed in the command output. Next, let's check the connectivity of the SRv6 TE policy. Checking the connectivity requires a special seed called end.op seed, where the letter O stands for OAM. This seed instructs data packets to be sent to the control plane for OAM processing. During the policy connectivity check, the head end adds the end.op seed to the segment list. Only the endpoint that generates the end.op seed can process ICMP ping and chase packets. As such, end-to-end connectivity check can be implemented based on this seed. In this example, one of the highlighted seeds is configured on P1 and the other is configured on P2. Now it's time to perform a ping. For example, we can run the ping command on P1 to ping the SRv6 TE policy, with the end.op seed configured on P2 being specified. The command output shows that the ping succeeds. Unlike the configuration on P1, we need to specify the end.op seed configured on P1 in the ping command to be run on P2. We can see that the ping also succeeds. This means that the SRv6 TE policy is successfully configured. That concludes our look at the implementation of SRv6 TE policy in the control plane. Next, let's see how SRv6 TE policy data packets are encapsulated. In this example, a ping is initiated from P1 to P2 to simulate packet encapsulation. We can see that SRv6 encapsulation is performed first, followed by SRv6 encapsulation. The source address is the loopback interface address of P1, which is also the previously configured SRv6 encapsulation source address. The packet is encapsulated with an SRh stack consisting of two seeds, one end.op seed and one path seed. The primary segment list is these two addresses. Because the first seed is the local end.x seed of P1, P1 does not encapsulate this seed to reduce SRh costs. That's all for this course on SRv6 TE Policy. We'll introduce various services supported by SRv6 TE Policy later. Thank you for watching.